Today I thought we'd take a look at one of the latest additions to Aurena, telemetry on the in-memory message bus. On the surface, it doesn't sound particularly exciting, but if you're building event-driven applications, it's one of those features that quickly becomes indispensable. It gives you the ability to see exactly how an operation flows through the system, where the time has been spent, and where things start to go wrong. As Aurena is built around an event-driven architecture, almost everything flows through the message bus. This gives me excellent decoupling between components, but it also makes understanding the path of a single operation much harder. Traditional IDE debugging becomes far less useful because the publisher often has no idea which components will ultimately handle an event. To solve that problem, I added distributed tracing to the message bus. The implementation itself is fairly straightforward. It uses the standard activity source.start activity pattern that anyone who's worked with OpenTelemetry and .NET will already be familiar with. For Aurena, it doesn't really make sense to run a cloud-hosted dashboard. This is a desktop application, not a cloud service. Fortunately, there are some excellent local options, one of which is the .NET Aspire dashboard. It's a self-contained Docker image from Microsoft that you can launch with a single command in the terminal. Once it's running, you get a waterfall view of every traced operation. If you've ever used Azure Application Insights, it'll immediately feel familiar. One of the nice things about everything running in a single process, rather than a cross-process microservices architecture, is that propagating a correlation ID becomes much simpler. That said, in-process doesn't mean it's completely free, and it's worth being honest about that. Aurena deliberately gives every subscriber its own serial processing queue. Publishing an event schedules work onto those queues using task.run. The producer span is disposed by the time the async handler runs, and the shared drain pump batches work across publishers. So the ambient current is gone or belongs to a different event, hence we capture and reparent explicitly. To keep the trace intact, I capture the publishing activities context at the point the event is published and carry that context onto each subscriber queue. Every subscriber then creates its own child span using the captured parent. The end result is exactly what you'd hope for. Every published operation becomes a parent span, every subscriber becomes a child span, and the entire fan-out appears as one coherent trace. Without doing this, every subscriber would start its own orphan trace, and the whole picture would be lost. The next challenge wasn't collecting traces, it was reducing noise. When I first opened the Aspire dashboard, it was absolutely flooded with events. Now, this wasn't exactly surprising, as Aurena has a handful of extremely high-frequency messages, particularly the events driving the real-time spectrum analyzer and the media track position change event, which fires continuously while a track is playing. These spectrum events were easy to deal with. They use a dedicated publish sync path that is designed specifically for high-frequency fire and forget messages. So I simply don't trace that publish path at all. Those spans never get created. The track position event was a little more interesting because it's something I might actually want to trace occasionally. So to do this, there are a couple of obvious options. One approach was to add a marker interface that effectively opts an event out of tracing. It's a nice, clean design, but it has one big drawback. If I later decide I do want to trace that event, I need to change the code and rebuild the application. Hardly ideal. Instead, I settle for the second option, a deny list. It's not quite as elegant because it matches event type names from configuration, but it gives me something more valuable, operational flexibility. If I ever need to trace one of those events again, I simply remove it from the configuration and restart the application. No rebuild required. The telemetry dashboards themselves can filter events after they've already been collected, and you could certainly rely on that instead. It gives you more flexibility because nothing is filtered up front, but the problem is it doesn't solve one very important issue. Reducing noise is one of the most important parts of adding telemetry to any application. Noisy traces are harder to read because the interesting operations get buried beneath thousands of routine events. More importantly, they can make your telemetry grow incredibly quickly. In a local environment, the Aspire dashboard keeps everything in memory. Eventually that buffer fills up and older traces get evicted. That can be frustrating because it can quite happily happen right in the middle of investigating a trace. You're looking through it, suddenly bang, it's gone. In a cloud environment, things can get even more expensive, and I mean literally more expensive. Cloud providers are not silly. They know just how easy it is to generate enormous amounts of telemetry. Now, call me cynical, but I have a strange feeling that they charge a significant premium for log storage because they know damn well that developers will forget to filter their logs effectively, at least until they receive that rather unpleasant bill. This is why it's really worth validating your telemetry locally before you ever deploy it. Tools like the Aspire dashboard make it very easy to identify noisy events long before they reach your cloud system. So, what has all this actually added? Well, quite a lot as it turns out. Every operation can now be traced from the moment it's published until every subscriber has finished processing it. Exceptions appear exactly when they occur. Each handler is individually timed, and it's immediately obvious where the application is spending its time. Perhaps more importantly, the message bus has stopped being a black box. I can now watch complex operations flow through the system in real time and understand exactly which components are involved and spot performance bottlenecks long before users will ever notice them. For something that only took about an afternoon to implement, that's a pretty good return on investment.